it's a developer's guide to exploring and visualizing IoT data, but it would be really nice to see the whole stuff. No idea. Sorry for that. But maybe I can just zoom out one step. Okay, now you can see the whole slide, at least. So I'm basically starting to teach how to grab data and run a little ETL process stored in a NoSQL database and analyze it using ApacheSpark and ApacheSpark SQL. And the last thing I'm teaching there in the last week is principal component analysis. So it's if you want to become an IoT data scientist, maybe it's a good course. But that's all about central nervous systems of IoT systems. I want to tell you more about the brain of IoT systems. And we will run a little demo, but maybe later. So first question I have is, who of you are machine learners? Okay. Software engineers? So what else are you? Can you just tell me what you are? Just who didn't raise? Yeah?
I raised my hand for machine learning.
Excuse me?
I raised my hand for machine learning.
Ah, sorry. Okay. So anyone who didn't raise is alright?
I'm marketing.
Online
marketing.
Okay. Online marketing. But are you analyzing data?
Yeah.
Okay. You?
I work for industry.
Okay. Okay.
Human-computer interaction.
Okay. Any Python programmers in here? Java? Scala? R? JavaScript? C#? Okay. Anything else? Excuse me? Closure. Oh, okay. Yeah.
MATLAB, C, assembler.
Oh, okay. Oh my God. Okay. So machine learning. Normally, if you talk about machine learning, it's on historic data. You're running batches against data, and you train a model, and you come up with a model. So in IoT, we are using a lot of online learning. So online learning has two components. One is stream processing, and one is incremental model update. And here are the pros and the cons. So in online learning, you have low storage costs. Normally, you don't need to store the data. You have always accurate real-time models, but not all algorithms are supporting incremental data processing. Therefore, the software is limited supporting those. And if you come up with a better idea, a better algorithm, your data is gone. And also, we will see that later in the little demo, the compute power has to be in line with the data arrival rate. So I'm running a neural network on my machine, but I have to throttle down the data, otherwise the data will get trashed. The other thing is, on historic machine learning, all the algorithms start with historic machine learning. There's an abundance of open source software, scikit-learn, R, closed source like SAS and SPSS. You can come up with better ideas, better algorithms, try things out in batches, and also batch processing means you do not have to cope with any data arrival rates. You just store it on a cheap storage, and then you are basically done. But you have to pay for the storage. So one example is a client in Switzerland, a hospital, where we store EEG data of 10 years of 10 patients in the brain ICU, and it costs $500,000 USD just to store the data. Not because IBM is expensive, because it's a lot of data. And we do only batch model update, which is often not a problem, but sometimes you want to have highly accurate and models. So what is this formula? Any ideas?
Linear regression.
It's nearly linear. Yeah, it's a linear regression model. Can you be more precise?
With regularization.
It's some sort.
Arima.
It's
Arima.
Arima. Yeah. Autoregressive integrated moving average. It's only there to tell you that's one of the state-of-the-art machine learning models for time series forecasting. And I want to tell you how to use deep learning for those tasks. So just to get everybody on the same page, this is a hypothetical data set of a manufacturing pipeline. So it produces some parts, and either those are healthy or broken. Healthy means outcome 1 and broken means outcome 0. And can you tell me a simple rule in order to predict the outcome?
Vibration
Vibration, okay, is?
greater than
3,000.
Okay, is 3,000 a good threshold?
100.
60.
I have 100. I was also guessing 100 is maybe a good value, given that it's very small data set. Of course, in a real-time scenario, if you do it in a white box modeling approach like this, you would sample the distribution of the columns and then calculate the threshold. But that's already a good start. And maybe you have some insights about the machine, and you can tell if it's bigger than 100, then something definitely is broken.
One could also argue that if the part number is greater than 107, it's going to fail.
Yeah, that you could argue, but I think the model won't perform too good, no? So what is this one?
Linear regression.
It's linear regression, okay. So the idea is you can learn model parameters for training a prediction model. Can you tell me the model parameters? A, B, C, and D?
Interception coefficients.
Yeah, so just tell me the numbers for that data set. You can guess, and you can also tell me 1 or 2, like starting 1 or 2. B and C are pretty easy.
0 would be.
Yeah, 0 is
Yeah.
B and C, I would guess, are 0, and A and D. There are multiple solutions, because the degree of freedoms, but one solution is okay.
Something like A is 1 and B is minus 1 divided by 100. Something
Not
like that.
bad.
It would be the slope, like the slope of the, because of the maximum vibration, right? D would be the slope of the line. So this equation of the slope could be 1.
Okay. Yeah, the thing is, it's a bit hard to get 0 and 1 because it's linear regression. So what is this?
Logistic regression.
Yeah. So what is the logistic regression? You take a linear regression model, you use the sigmoid function, and so sigmoid basically squashes any range from minus infinity to plus infinity to 0 and 1, and you can learn a threshold, and then you get a binary classifier. Okay, so that's supervised machine learning, binary classification, what we are doing here. Is that clear to everybody? Okay. So who of you has worked with artificial neural networks before? Okay. Also in production or playing around only from production use cases? Okay. So the idea why I introduce logistic regression is because it's really easy to understand artificial neural networks if you understood logistic regression, because this is a single neuron in an artificial neural network where you basically so we basically have x1 to xn. You cannot read it, it's x1 to xn. Those are the input features or the columns of the table. You have the weights. So you basically multiply all the input data with the weights. Then you put it to a transfer function. It's always sum in my experience. And then the important part is the activation function. You can use sigmoid there. And then you have one neuron. This is inspired by a biological neuron. So this is a biological neuron. It's one cell. You have a nucleus, which is also very important for long-term learning. But in a trained neuron, data arrives here in the dendrites from upstream neurons. The processing takes place in the neuron by calculating a function, a biological function, and whenever that function is fulfilled, it generates a spike that travels downstream this axon, and here this neuron connects to downstream neurons, and those are connected using synapses. Have you heard about synapses before? So those are biological signal transductors, and in contrast to artificial neural networks, the synapse in an artificial neural network is nothing else than a multiplication, and in a biological neural network it's a complex biochemical process, and if you simulate that process you need processing power of that laptop for one single synapse. So it's far, far away what we are doing in artificial neural networks, don't be scared. So that's a little small feed-forward neural network with one hidden layer. So in this case this would fit our data because we have 3 input columns and we have a binary outcome. So we use this out of the box for training it. And the idea is we just show this neural network all our data, and eventually all the weights are adjusted that you can get a binary classification model out of such a neural network. So why is there a hidden layer? I'll tell you that in a second. So I've implemented now one neuron in Python. Anyone in here who doesn't know what vector-vector multiplication is? No? So everybody knows what vector-vector multiplication is. So I'm using NumPy here. It's a linear algebra library of Python. X is the input data,